Warahmatullahi wabarakatuh. Hello everyone, hope everybody's doing well. We're gonna continue what we stopped at last time, speaking about kinetic energy and gravitational potential energy at work. The last thing mentioned in this chapter is a topic that we're gonna discuss with the name of power. And it's very simple, since you guys already know what power is and we took it in unit 2. It's not something that's complicated here at all. Just a quick reminder to what the topic is and how it works, because back when we took it in unit 2, we were speaking about specifically electric energy, if you guys remember with me. But the idea is power exists not only in electric energy. Power as a concept is something that exists as long as there is energy. If you remember with me, we defined it back in the day with a formula that said power, okay, equals the amount of energy that you have over time, because you need to divide your energy by something that refers to time, depending on what it is, and usually we use the second in this case. But yeah, power is just something that indicates to you how much energy you're spending in every second, and it changes the idea from energy being a value into something else that we call a rate. We said whenever you take any value, any quantity, and you divide it by time, it becomes a rate. And by a rate, it's basically just something that identifies to you how much energy do you spend every second. All right, so assuming that we have a machine, and I can tell you that I made this machine work for a whole hour, and in this hour, it spent 600,000 joules, for example. That's the energy the machine spent. I can come to something that's easier. If I take 600,000 joules, the number that I gave you right now, and I divide it by time, and by time is, I tell you, since I mentioned in this question that it has worked for 1 hour, okay, I can basically change it from being something that just tells you how much the machine spent in total inside this full hour into how much does it spend every second. And this is a very good indicator for consumers, for users, for even manufacturing companies to know their devices, how much energy do they need per second. It's easier than knowing how much total energy it needs, because then you need to identify the time in which you did the tests in. But if I take, for example, the energy that I have, which is 600,000, okay, and divide it by the time, and since my time is 1 hour, I switch that to seconds. I need to multiply it by 60. 1 times 60, and then it becomes minute, and another 60 to become seconds, because 1 multiplied by 60 will turn it into 60 minutes. But I'm not trying to figure out the minutes, I'm trying to figure out the seconds, and 1 minute has 60 seconds inside of it. 60 times 60, it gives you 3,600. All right, which means the machine worked for 3,600 seconds, and it spent this amount of energy, which is 600,000 joules. Now, if I take that number, I put it right here, and I divide the total energy with the total time spent, as you can see right there, the answer I would be getting to is 166.66 and joules per second, which is kind of just a simple calculation that tells you that, wallahi, as long as this machine is turned on, then just remember that every second while it's turned on, it's spending 166 joules. That's what I mean by joules per second. I'm telling you how many joules, how much energy it spends every second while it's working. And that's the total idea, that's the entire idea about power, sorry. It's just basically a small calculation that we do to identify our devices and appliances and machines, depending on what we're manufacturing or consuming, how much energy do they spend in 1 second. Therefore, if you can tell how much energy your machine spends in 1 second, if I tell you that you turned it on for 30 seconds, it's no problem for you to figure that out, how much energy you will have spent in total. If I told you, no, not 30 seconds, I left it over for 30 minutes. If I tell you that I left it, no, more than that, I left it over for 2 hours, it doesn't matter to you. You know how much it spends every second, so you just need to multiply the numbers. It's very easy. All right, and that's why power is a very important calculation when it comes to energy usages, because it makes things seem very simple. Like when you're buying a device and you want to know, okay, does this device spend a lot of energy or not? Just check the power. If the power says this device spends 3,000 joules per second, then you have your answer. If it says 500 joules per second, you have your answer. So it's a very important calculation in physics in general, and it's more reliable in manufacturing and labeling stuff than energy. Energy is very vague. I tell you how much energy something spent, well, there are other factors that might affect it. The biggest one is being time. Because if I tell you that a car spent 5 million joules, well, you need to know in how much time, what's the distance it moved in, whatever. It brings a lot of questions with it. While power connects everything to time. So if I tell you the washing machine is working with the 3,200 joules per second. That's it. You know that every second while it's on, it uses 3,200 joules, and then you can do whatever calculation. The small ideas I want you to know about power, other than the concept itself. Okay, the main unit for power, okay, scientifically, power in reality is how many joules you spend every second. So whenever if you answer a question and you calculated power, okay, and you told them that the unit for it is joules per second, the examiner has no other option than saying that your answer is correct. But this thing that we call joules per second also has another name that people use more commonly. You see it often even on devices and stuff. They call it watts. Okay, and watts are joules per second. They're the exact same thing. So whenever you're answering a question, you can either write the unit finally as joules per second, or you can put a small w, which refers to watts, which is also completely correct. All right. Now we're jumping straight to a question because the topic is simple and there is no need to make something complicated simple. Something simple complicated. It's already simple. So we go look at a question like this one. It says that photographer shows equipment used to generate electricity from renewable sources. It's just somebody using two things to generate electricity. This is going to be important in chapter 17, which we're going to start next video, inshallah. Just take a look that there are other ways to generate electricity other than fossil fuel. This guy is using wind turbines. He also has if you can see right here, he has a panel of solar cells. So he's just trying to generate electricity. We're not very interested in that. On a windy day, which means this one will start spinning. All right. The wind turbine transfers 78 watts of power. Notice that in this question, instead of saying that power is joules per second, he said that power is watts. And remember, those two things are equal. They're the same thing. This one and this one. Joules per second. Watts, doesn't matter. That's the unit for power. State the equation linking power, energy transferred, and time. Your answer should be simply power equals energy transferred divided by time. No issue at all. Okay. Calculate the amount of energy the turbine transfers in 10 seconds. The time is given to you right here to be 10 seconds, as you can see as displayed. The power has been given to you up there. So we have our power is 78 watts. Our time is 10 seconds. All right. And we're just asked to calculate the energy. You go back to the main formula up here. It says power equals energy divided by time, but I'm not trying to calculate power. I'm trying to calculate energy. So we reshape it. It becomes energy equals power multiplied by time. I just rearranged the formula that we have on top here to make it easier for us to use. And therefore, the amount of power is 78 watts multiplied by the time, which is 10 seconds. And it's going to give you 780 joules because we're calculating energy, and the energy for, the unit for energy is just joules, not joules per second. Huh? Knowing that last small section that I just spoke about, which is power and how you deal with it, that's it. You've already finished the whole chapter, covering up the main topics in which we went over, starting off, first of all, by a topic that was called work. We said work was force multiplied by distance, if you remember with me. And we said this whole thing of force multiplied by distance, we calculated it in the unit of joules, making it some sort of energy. And then we said there are other energies that have relations to do with movement, starting off with something we call the kinetic energy. And we said the kinetic energy was half multiplied by the mass of the object multiplied by its velocity squared. And finally, we said that there is another type of energy that we needed to cover, which was called the gravitational potential energy. And we said the formula for it was mass multiplied by height and multiplied by gravity. And those three things, you have to know all of them. And the extra one, which we took today right now, it just says power. I'm going to write it very small here, equals energy divided by time. No matter what energy you're using here, the energy can be a calculation of work, the energy can be kinetic, the energy can be gravitational potential energy, it can be electric energy from the unit that we took in unit 2, it doesn't matter. It's just something that identifies to you how much energy is being used per second, and it doesn't matter what kind of energy I'm talking about here, it works for all of them. Now, even though this concludes everything you need to know, we need to deal with a special type of problem. Okay, which is what if the question itself starts mixing up all of these things that you studied, I'm not talking about power. Power is usually a calculation asked at the very end. No problem with it. You're just gonna take an energy over time, or sometimes it's the other way around. But I'm sure you're not gonna struggle with this. The tough thing that you need to know and understand properly is, what if the question gives you a scenario that has multiple energies together, or it gives you a scenario which has an energy that changes into another energy mid-question. You need to understand this example usually occurs when we're talking about free fall, objects falling down, and it's very common, by the way. That's the hardest thing they could possibly ask when it comes to this chapter. So I've prepared a few questions from past papers to do with this exact idea. We're just gonna discuss it, solve it. Once you understand the core idea of it, it's pretty simple. And the core idea is easy. We spoke about something called the law of conservation of energy. We have discussed this, and this law tells you that energy cannot be created, it cannot be destroyed, but it changes from one form to another. And I'm gonna focus on free fall examples, because if you connect them in your hand, everything else kind of becomes easier to that. So imagine if you have a shelf, this is a wall, and connected to it you have a shelf. That's a very big shelf. I don't think the shelf needs to be that big. Just a small shelf like this, and you've placed a book on the very edge. Excuse my drawing, we already know it's not the best. Just gonna... okay. And I don't know what happened, but suddenly this book slipped from the edge and it started to, I don't know, get to the side, and then suddenly it started falling down. The idea is, what's the main factor making this book fall down? The only right answer when it comes to this is because there is something called gravity. Okay. We understand that everything that's on Earth has to fall downwards if there is nothing stopping it from that. All right. And if you discuss that in the idea which we spoke about when it comes to energies, we call this type of thing that's dragging things downwards as long as there is height, we call it gravitational potential energy. Okay, so this book has the energy, or has the potential to fall down if it's put in the right conditions, meaning the shelf right down below it that's stopping it from falling all of a sudden disappears. I'm talking about this shelf right here. If this shelf disappears, then the only thing that could happen to the book is it will fall towards the ground. Therefore, while it's being put up here, and there is a certain height between it and the ground, there is gravitational potential energy stored inside the book. Okay, now assume that this book, okay, suddenly is off the shelf and it's about to fall to the ground. The only factor that's making it go towards the ground, as we agreed, is gonna be gravity. All right, and since that's the case, I want you to understand that all of the gravitational potential energy stored inside the book will convert into movement, because the book won't be up here standing still. No, it will be going downwards, moving towards the ground. What's the energy of movement called? We identified it as kinetic energy. So what happened in this scenario? At first, the book was on the shelf. It can fall down, but it's not moving. Therefore, it has gravitational potential energy stored inside of it. And then suddenly we take it off the shelf, and once it's off the shelf, it starts moving. And because it's moving, it gains the energy of kinetic energy, which is the energy of movement. This example happens in many different ideas. If you think about it, if you hold something literally from your hand towards the ground and let go of your hand, you'll watch it turning from energy stored with the potential to fall down, which we identify as gravitational potential energy, into as soon as you let go of your hand, poof, it falls to the ground, and that's kinetic energy. This is a way in which energy can change from one store, because at first when it was held up, it was gravitational. Oh, I'm not trying to write on this one. At first when it was up there, it was gravitational potential energy, and the moment it falls or starts falling, it starts turning into kinetic energy. This type of question, they bring it very often. Okay, why? We'll see exactly why when it comes to the question, but sorry, what I was trying to say here is, why do you need to understand, and why do we take this whole thing to begin with, is understand that the only thing responsible for this book's movement is the fact that gravity is pulling it down. Okay, so if gravity was pulling it down using gravitational potential energy with an energy of 5 joules, then please understand with me, the energy the book is gonna move with afterwards is gonna be 5 joules, because nothing else is responsible for moving the book. Whatever was stored in its gravitational potential energy will turn into energy of movement, which we call kinetic energy, and that's it. No energy will come from anywhere, no energy will get destroyed or whatever. Okay, so imagine if instead of putting the book right here on this shelf, I think I'm gonna have to add another page to explain what I'm trying to say, but imagine if instead of putting it on that shelf, here we have a page prepared right here. This is the first example. And the book is on this edge. Imagine if I take the exact thing, okay, but this time I place the book on a higher shelf. Okay. You guys need to excuse my drawing. I was never good at this. Okay, and you take it and place it on top of a higher shelf, like this one. This one has some movement to do. This one has more movement to do because it's higher off the ground, and this causes automatically the height of this one to be smaller than the height of that one. So let's give numbers to just make the example easy to identify what I'm trying to say here. Imagine if the height between this and the ground was 2 meters, and the height between this and the ground, because it's put on a high shelf, imagine it's 3 meters. Both of them are placed in the exact same planet, Earth, therefore they both have the gravity of 10. All right, and the last thing you need to concern yourself with, since both of them are placed in the exact same place, is mass. Okay, and for the example, I want to tell you that both of the books are exactly identical, making both of them have the exact mass of 1 kilogram. Okay, let's see which one has more energy. The formula for gravitational potential energy would suggest that it's mass multiplied by height, and gravity. Okay, mass times gravity times height. Going to do the calculation for the first book. Okay, let's call it A. When it comes to A, we're gonna do the calculation for it. The mass of the book is 1 kilogram. The height it's placed away from the ground is 2 meters. And the gravity, we're gonna assume it's 10. Multiply all of these together. 1 times 2 is 2, 2 times 10 is 20 joules. So if this book falls down, it will fall down with the energy of 20 joules. It will move with the energy of 20 joules. Look at the other book, it's placed at a higher place. Okay, the mass of it, again 1 kilogram, gravity is the same for them, 10, but the difference is this one put 3 meters high. So let's calculate it and let's call it book B, and it would be 1 times 3 meters times the gravity, which is 10. Okay, and if you multiply all three of them, they will give you 30 joules. Now, the difference is this one is put on a higher place, therefore it has higher energy to move with afterwards. This one was put in a lower place, therefore it has lower energy to move with afterwards. If the books start falling off the shelf, all of this 20 joules will turn into movement because the book will be moving, so it will all turn into 20 joules, but of who? Of kinetic energy. And if this one starts falling down, all of it will turn into 30 joules of kinetic energy. And that just shows you the conversion between some store of energy to another store of energy. Hopefully with the examples I'm going to display, it will get clearer, but that's the idea we're trying to get to you. Now, I brought this example in the mock exam last year, because I like the idea of it. It covers a lot of stuff to do with this chapter all in one question. It says the car is launched from point A, and you can see where point A is here, this level down here, meaning it's before it rises up or anything, because look, point C is at the very top, point B is at the very end right there, but it's launched from a level ground. Okay, the photographer, in the photograph, accelerates to point B, rises over to point C. So it's 3 stages from here to there. And then once it reaches point B, it starts going up all the way until it reaches point C. All right, but we don't need to worry about that. It's just explaining what happens in the scenario. Each loaded car has the mass of 2,000 kilograms. So the mass is given to you right here if you need it in any calculation. Point C is 128 meters above. So it's kind of telling you if you need height to calculate stuff, remember it's 128 meters. All right. And then if you continue downwards, it says state the equation linking gravitational potential energy, mass, height, and gravitational field strength. You would need to use the exact words mentioned right here, saying that the gravitational, I'm going to write it in short, potential energy equals the mass multiplied by the height multiply by the gravitational field strength. But try to remember with me that you need to write the formulas in full letters or full words. Sorry, I'm just doing this to not waste much time because you get the idea I'm trying to say. So instead of saying GPE, try to write gravitational potential energy as a full word. Instead of saying gravitational fields, instead of saying gravitational field strength at GFS, write it as a full word, which is gravitational field strength. Put it right here and here. Show that the gravitational potential energy gained by the car when it rises from point B to point C is 2.6 megajoules. Well, look, it's very easy. Again, why? Because you know the mass of the car is 2000. You know that the height it rises is 128. And you know we're doing all of this experiment on Earth and gravity on Earth is 10. So therefore, it's just asking you what's the energy of the cart when it reaches the very summit. And we understand that the higher you go, the more gravitational potential energy you gain. At first, right here on the ground, it had 0 because there was no height. By the time it reached to the very top, I'm trying to figure out how much gravitational potential energy is at the very top. Knowing all the numbers, it's nothing complicated. Gravitational potential energy is to us the mass, which we know that it's 2000 kilograms, multiplied by the height, which is right here given to us as 128 meters, and the gravity on Earth, which is 10. You just need to multiply all three numbers together, and no problem. If you multiply these numbers together, you end up with the final answer of 2,560,000 joules. Okay, but the question tells you that show it that it's about 2.6 megajoules. All it did is basically round up the number and you got a number that's close enough to it. If you need to switch this number to mega, I told you mega is a million, if you remember with me. Okay, therefore divide this number by a million, it would end up being 2.56 megajoules, and it's very, very, very close to the number it suggested, recommending that your answer is correct. Moving forward, it says the car gains kinetic energy when work is done on it by the launch system between A and B, meaning the only reason it moved at the beginning is because it got pushed forward using some sort of work or whatever. Assume there are no energy losses. State the minimum kinetic energy that the car must have at B before it reaches C. All right, now you need to understand that in order to make something move upwards, you need energy. Okay, to make it go from the very bottom right here to the very top right there, you need energy. And how much energy do you have at the very top? We calculated that to be 2.56 megajoules. Meaning, if you want to push something from the ground to all the way up there, you need 2.56 megajoules, because that's the amount of energy you need to fight over or against, basically, if that makes sense. And the car is being launched from here, and that basically is just asking you how much energy do you need to rise from point B to point C. Now, when it comes to free fall, you don't need energy because everything gets pulled down by gravity. That's totally normal. But when it comes to going upwards, you just need to counter it. If the maximum energy at the very top is 2.56, then for me to rise up there, I need 2.56 megajoules of energy in order to make it to the very top. So you don't need to do a calculation or anything. You already done the calculation in the previous one. So the minimum amount of energy is 2.56 megajoule. If you push the car with more than that, then it's totally fine. You will still make it upwards and you will have more energy left. How is the kinetic energy gained related to work? You just need to explain to it that the work done, and we already discussed this point, is always equal to the energy transferred. And since the launch pad made the work of 2.56 megajoules, then it's the same amount of energy transferred to the kinetic energy store. And that's something, again, I told you. Remember that all of these can be equal to each other in certain scenarios, and it's just testing if you know this point or you don't know this point. Okay, write down the equation linking work done, force and distance, and we already know that work from the previous lessons equals force multiplied by distance. No issue with that as well. And the launching system provides a force of 32 kilonewtons. Calculate the minimum length track needed between A and B for the car to reach C. Okay, so we understand. Look, it's trying to get confusing a bit here, but really not. We need to write down everything we know. We know that the force is 32 kilonewtons, which is, if we switch it to normal newtons, is 32,000 newtons. Okay, we know that the amount of energy that we need in order for us to climb upwards is 2.56 mega joules. All right, and it's asking us basically to calculate what's the minimum distance that we need in order to create this energy. All right, and it's very simple. The formula says work. Try it with another color. It says work equals force times distance. I'm trying to figure out the distance, so all I need to do is leave it on a side on its own. It becomes distance equals force, work divided by force. And I just need to put the numbers in the right position. Now, instead of work, I'm gonna use the energy that I need to go upwards, because we agreed that the work done is the same as the energy. Okay, so in this question, because I already figured out the energy at the top and I used it again, I can use it here one more time with no problem. So I need to divide 2.56 mega joules by the force of 32 kilonewtons. This is what you need to do, and it will give you the final answer, but I'm running out of space here. I'll try to do it right here, maybe. Yeah, I'll try to do it right here. I think this fits. Sorry for it being unorganized. I didn't expect it to take this much space. Let's do it easily, okay? Now look, we need 2,506,000 joules, okay, divided by 32,000, and it's gonna give us the answer right here. Let me do that. The answer that I got is 80, and because we're calculating a distance, we're talking about 80 meters. And one last thing, just don't let it confuse you. All I did is use the number instead of it being in megajoules, as you can see here. No, I want it in normal joules. So remember, the word mega means a million, so I multiplied it by a million. I ended up with this. And then secondly, it gave me the force in the question up here. It gave it to me as kilonewtons. I don't want to deal with kilonewtons. We deal with newtons, so I had to multiply it by 1,000 in order to make it normal newtons. And you just need to do your calculation, the division, whatever it is, and you end up with the final answer being 80 meters. It tells you lastly that sometimes the car does not reach C, but it rolls backwards to the start. This can happen when it becomes windy or the track becomes wet. Explain why these conditions could cause the car to stop before reaching C. Because I told you, in order for you to push it up, you need to generate a minimum energy that pushes forward, or a minimum work of 2.56 megajoules. But if it's windy, for example, then, you know, in order for you to reach the 2.56 megajoules, it's not as easy because there is force pushing you backward. You need a bigger force to push forward. There are many ways for you to answer this question, and it's up to you. Basically, you just need to use this number as a reference, saying, for example, if the launcher, you know, it does the work of force multiplied by distance, okay, and the distance, you can't change that. You know, the distance is 80 meters, but the force that you push with, it might be affected, because sometimes it pushes with 32,000 newtons, such as in this case, but this might not be enough. If the weather was windy, you might need to push with more than 32,000. Does that make sense? You need to push maybe with 35,000 if the weather is windy, because it's harder for you to push forward with wind causing drag, affecting you backwards. There are many ways for you to answer this question, but you just need to focus about the fact that the force is going to be affected with the wind and the wetness of the ground, or whatever it is, okay? Because the distance stays the same. The distance will always be 80 meters between you and the launch going upwards. Last question, inshallah. And again, it mixes up a lot of different ideas when it comes to using three of them: work and energy and kinetic and gravitational energy all together. It says the golf ball has a mass of 50 grams. So you have the mass right here. Just focus, it's grams. You need to change it to kilograms. Keep an eye on that. And and he transferred 56 joules of energy to it. Okay. State the equation linking kinetic energy, mass, and velocity. We already know that it's kinetic energy equals half times mass times velocity, but don't remember the power of 2. Okay. Calculate the initial velocity of the ball, and no issue at all. We just need to look at the mass of the ball, which is 50 grams. We need to look at the energy he gives it. All right, and we just need to do the small calculation right here using the formula on top of it. So the energy received by the ball is 56 joules equals half multiplied by the mass of the ball. Heads up, I told you you need to switch this one to kilograms, right? We have the number as 50 grams. Okay, in order for us to switch it to kilograms, we need to divide it by 1,000. Okay, it becomes 0.05 kilograms. Okay. And we need to multiply it by the velocity, which we don't know, but it has a power of 2 on top of it. First of all, multiply half and 0.05. Okay. Gives you 0.025 multiplied by velocity squared equals on the other side 56. Put everything in its right position. I'm trying to calculate this one, leave it on the side on its own, take this one to the other side as a division. It becomes 56 over 0.025 equals on the other side velocity squared. All right, divide those two together. And the answer you're going to receive is this number. And then finally, you have a square. So how do you get rid of the square? You need to use something we call the square root. So you just need to put the number that we got, which is 2,240 underneath the square root. And it tells you that the velocity of the ball, as soon as he hits it, it becomes 47.32 meters per second. Okay, I hope it's clear. All I needed to do at the end is to put this number under the square root in order to get rid of the power of 2. And this is the initial velocity, meaning as soon as he hits it, obviously when you shoot a ball, when you strike something, the moment you hit it, it goes with so much speed, and then with time it slows down. So the moment he strikes it with the golf club, it becomes this fast, 47.32 meters per second. All right. Anyways, we continue with the video right here. The height, it tells you that at its highest point, because it's a golf ball, it got kicked, so probably like went upwards. At its highest point, the ball had gained 12 joules of gravitational potential energy. State the kinetic energy of the ball at its highest point. Okay, so since the ball was kicked upwards, and we're talking about the moon doesn't have air resistance, it doesn't have anything to slow the ball down, except for once it gets kicked, it goes up. And when it goes up, the moon has gravity, therefore it will try to pull it down. It's kind of a simple calculation here, since we know that the total energy it moved with at the beginning is 56 joules. All right. And now it went upwards by 12 joules, which are going to be used from the original 56. The kinetic energy at this point is simply just doing 56 minus 12. And it's going to tell you that the ball has 44 joules at that point. Okay, and we'll go back and discuss this point in a little bit once we finish the question. Why do we do this? State the equation linking gravitational potential energy and all of that. It's just gravitational potential energy equals mass times height times gravity. Okay, and calculate the maximum height the ball has reached. It has given you right here the gravity to be 1.6 Newton per kilogram. You already know the formula. You know that the energy it has gained at that point is 12. So you just need to do a small calculation based on everything that you have. Therefore, simply you just need to rearrange the formula. It says GPE equals mass times height times gravity. I'm trying to calculate height, so take both of these to the other side. It becomes height equals GPE divided by mass times gravity. Okay, and then finally, putting everything in its right place, it just becomes an algebra problem. It says that height equals the energy in which it went upward, which is the gravitational potential energy given to you as 12, all right, divided by the mass of the ball at the very, very, very top. If you scroll up, well, I'm just lazy to do it. It's 0.05. Okay, I'll do it. Here, 50 grams. We had to switch it, and it became 0.05 kilograms. Okay. Multiplied by gravity, but we're not on Earth, so we're not going to use number 10. No, we're going to use the gravity of the moon, which is 1.6. And the final answer is 150 meters, meaning that the ball got kicked up 150 meters in order for it to happen like this. And by the way, the number makes sense because you're not on Earth. If you kick a ball upwards on Earth, with the energy it said 12 joules, it won't go up much, but because he's on the moon, there is way less gravity. It just takes a small hit for the ball to start rising up before starting to drop down. That's why it went all the way up 150 meters. The last question says, suggest why the ball traveled further on the moon than it would have done on Earth, and you can answer this like saying by, for example, that the value, let me write your answers, the value of gravity, or G, okay, and we're talking about on moon, is lower on the moon. Okay, that's 1 point, sorry. Remember, the question has 2 marks, you need to add another point. And for the other one, you could just basically recommend it with any other way that might come to your head. You might say that, for example, the time of rising upwards is more, but some answer which I like a lot, and I said it earlier, on the moon there is no air resistance, okay, which, you know, allows for further movement. And that would give you a full mark if it comes to answering such a question. Okay, that's it for chapter 16, and that's it for this video. This just makes, if you understand everything we discussed in the previous classes and find no problem in solving such problems, that's it. You pretty much understand the full chapter. I hope this was an easy experience rather than a hard one with the videos and everything. And yeah, I guess we'll stop right now and we'll continue next time. Thank you for watching, and I hope you understood everything we spoke about. Take good care of yourselves. Bye bye.